6 months ago, I presented a monochrome rotating display. The response was very positive, and I was asked again and again whether the concept could be extended to a color display. I accepted the challenge and would like to present a full color rotating display in this video. The design files with all the details, including the software, are published in a GitHub repository so that a replica is possible. This video, after a demonstration of the display, I will go through various design aspects and explain technical details. The display has a diameter of 120 millimeters. It can display color images, including animated GIF images. The display has a Wi-Fi connection and can be controlled via a web interface. Please note that the rotation of the display leads to disturbances in the video as the frame rate of the video overlaps with the rotation frequency of the display. These disturbances are not visible when looking directly at the display. However, I've tried to set the parameters of my video app so that the interference is as low as possible. After switching on the display, a start screen appears with the name of the Wi-Fi network and the IP address of the web interface. If you enter this address in a web browser, the web interface opens. It enables wireless control of all functions of the display. Configuration data and image data can also be loaded onto the display. Various operating modes can be selected using selection buttons, which are visible here in the middle of the screen. The first operating mode is an analog clock. A still or animated image can be displayed in the background. This can be loaded and selected on the configuration pages of the interface. The second operating mode is a digital clock. The digital clock simply displays the time and date and also the day of the week. If you want to display a logo or an animated image in addition to the digital time, you can select the third operating mode. I have selected the animated image of an aquarium. The next mode is the weather mode. In the weather mode, you see the time, also the temperature and humidity. I've selected my location here in Germany, and now let's change that location from Germany to, let's say, Lisbon. And what happens is that the background changes because the background gives an animated image of the current weather condition. That brings us to the last mode, which is simply an image mode. And here you can display a still image or an animated image. So let's turn off the display and have a look at the setup. What you can see now is the PCB of the display. It carries two microcontrollers, one ESP32 microcontroller up here and one RP2040 microcontroller down there. In the middle, there is a row of 56 RGB LEDs. The display board is powered by a power supply board, which is underneath the display board. In the middle of the power supply board, there is a motor which drives the display disc. Furthermore, we have the electronics for the wireless power transfer, and there is some electronics which drives the motor. Let's take a closer look at the device. The picture shows the setup from the side and from above. The main components are labeled. You can see the display and the power supply board. The device is supplied with 12 to 24 volts. Depending on the operating voltage, the power for supplying the LEDs can be changed. If the assembly is applied with a high voltage, a very high display brightness can be set. However, the brightness is normally sufficient even at 12 volts. In contrast to the first version of the display with monochrome LEDs, the color display uses SMD components only. This was the only way to achieve the necessary integration density. The circuit board has 4 layers. The 2 inner layers are grounding planes. I learned a lot about PCB design from the videos from Phil Salmony and Rick Hartley. I linked the videos in the description and can only recommend them. The display was produced in small quantities by a Chinese PCB manufacturer. In the upper half of the board you can see an ESP32-S3 microcontroller with a printed antenna for the Wi-Fi connection and a micro SD card reader. The controller is used as a web server and generates a website via which the display can be controlled. It can also download data from the internet to show it on the display. One example is weather data. In addition to controlling the display, the controller creates the image data to be displayed and sends it via an SPI interface to the second controller, which displays it with the LEDs. The use of an SD memory card makes it possible to store virtually unlimited amount of image data. 56 RGB color LEDs are arranged in the middle of the display. They are controlled by 7 LED driver chips, which in turn receive their data via an SPI interface. The SPI bus operates at high clock frequency of about 20 MHz, which enables a high update rate of the LEDs. An RP2040 microcontroller is located in the lower part of the board. This controller has 2 computing cores and has powerful and highly flexible programmable counters. It is therefore ideally suited to control the LEDs. One core is used for the very time-critical process of data transmission to the LEDs, and the other core for communication with the ESP32. The timing of the LED control is synchronized with the rotation of the display by a Hall sensor. A magnet generates a trigger pulse with each rotation, which starts the control sequence. Depending on the operating voltage, the display's wireless power supply provides a supply voltage of between 8 and 16 volts. 2 step-down converters convert this voltage into an operating voltage for the digital electronics of 3.3 volts and the supply voltage of the LEDs of 5 volts. This approach is far more efficient than linear regulators, which would have been a simple alternative. At the bottom of the board you can see 2 USB-C connectors that can be used to program the 2 microcontrollers. The display rotates at a high speed of up to 20 revolutions per second. To avoid vibrations, it is necessary to carefully balance the mass distribution on the display disc. The center of gravity must be exactly in the middle on the axis of rotation. In order to achieve this goal, the components are distributed on the circuit board with a view to symmetry. The components of the microcontroller and the power supply are arranged symmetrically to the vertical axis. Their center of gravity therefore lies on this axis of symmetry. The center of gravity is shifted to the center point with the help of 2 balancing weights, which are visible at the top of the board. The LEDs and 6 of their drivers have been arranged symmetrically to the center point. This means that their center of gravity is automatically exactly in the middle and does not need to be adjusted. What remains is the SD card slot and a driver chip. These components lie on an axis through the center point. With the help of a balancing weight, the center of gravity is also shifted to the middle. This picture shows the power supply board. SMD components were predominantly used on this board in order to increase the rebuild reliability and reduce the soldering effort. Only some components, which are only available in through-hole technology, have to be soldered by hand. In the middle of the board, you can see the motor that turns the display board. The motor sits on a separate carrier plate, which in turn is attached to the power supply PCB. This is necessary to set the correct distance between the display PCB and the power PCB. A step-down converter is also used to power the motor. This makes it possible to vary the supply voltage over a wide range. At the bottom right, you can see the electronics of a so-called Royer converter for the wireless power supply of the display. It is a parallel resonant circuit that is switched with 2 power transistors in push-pull mode. The oscillation frequency is around 120 kHz. The simple circuit is very robust and operates in a wide voltage range. However, there is one critical part of the Royer converter circuit that caused me major problems at the start of the development, namely the complex coil arrangement. This involves a so-called bifiller coil and a feedback coil, each of which have to be connected in the correct phase. However, all the problems with the arrangements were solved by designing the coils as printed circuit on the board. They are located on the back of the PCB, and in this way the circuit is really absolutely reliable and easy to replicate. Here is a view of the back of both boards. On the left side you see the power supply board with the printed coils of the Royer converter. You can also see the magnet that switches the Hall sensor of the display with each rotation. On the right-hand side you can see a photo of the back of the display board, an auxiliary board with the secondary coil of the wireless power supplies attached to it. In the middle of this auxiliary board is the mount for the motor's tray. The fact that this mount is now below the display means that the LEDs can be positioned also in the middle of the PCB. So much for the structure of the display. In the following, I would now like to go into some interesting aspects of the function of the display. First, let's talk about how it is possible to create a full still image with a rotating LED row. The rotating display uses a physiological effect called persistence of vision. This is why it is often referred to as a POV display. The effect is that the perception of an image lingers for a certain period of time. For example, if you look at a point of light, you can still see it for a certain period of time, even after it has gone out. If the point of light moves, it leaves a trail of light behind, so to speak. The following animation illustrates the principle for a series of LEDs mounted on a rotating disc. If the movement is slow, the light trail is still short. However, it becomes longer when the movement becomes faster. If the disk rotates very fast, a stationary image is created and the eye can no longer resolve the movement. The rotating display exploits this effect. It controls the LEDs so that they have the desired brightness and color at the right place. The color LEDs used have a width of 1.6 millimeters and are positioned 2 millimeters apart on the display. The principle of interlacing, which is also known from cathode ray tubes, is used to increase the resolution of the display. The principle, at the same time, increases the perceived frame rate and thus reduces flickering. The following animation illustrates the principle. Please note that the color of the LEDs in the illustration is just for clarity and has nothing to do with the color function. The display of color is explained in the next section of the video. The LEDs are arranged in a row from the left to the right edge of the display disc. However, the LEDs are not arranged symmetrically to the center, but shifted by a quarter of the spacing of the LEDs. If the LED row is now rotated by 180 degrees, the LEDs are shifted by half the LED spacing. In this way, the resolution is doubled. At the same time, the image is now updated twice per revolution, although not in full resolution. This increases the frame rate and reduces flickering. The image of the rotating display can be described most simply in a polar coordinate system. In such a system, the pixels are characterized by the radius and the radial angle. Given the 56 LEDs of the display, the radial resolution has 56 pixels. On the other hand, 240 angular positions are distinguished. In the polar coordinate system of the display, 56 times 240 pixels are therefore available, which corresponds to 13,440 pixels. When the image data is output to the LEDs, the radial LED data of each line is output one after the other for each angle. On the other hand, the images to be displayed are generated in a simple Cartesian coordinate system as shown on the right-hand side of the slide. The resolution used is 110 times 110 pixels, which corresponds to a total of 12,100 pixels. The image data in the Cartesian coordinate system must be converted into the polar coordinate system in order to display the image undistorted and upright on the display. The coordinate transformation is carried out with the help of lookup tables. In other words, the corresponding x and y coordinates for each pixel in the polar coordinate system are stored in a table. The transformation algorithm is therefore very fast. The routine runs on the RP32 microcontroller and is executed before the data is transferred to the RP2040. Now I would like to talk about the representation of color. The color LEDs each consist of a red, a green and a blue LED. Using so-called additive color mixing, any color can be displayed by mixing the three primary colors with different intensities. For example, the color yellow is created by mixing red and green with the same intensity. In terms of circuitry, however, this color mixing is quite problematic as the LEDs can only be switched on or off. This is why most color LEDs use pulse width modulation. This means that the LEDs are switched on and off at a frequency that is invisible to the eye. The brightness can be adjusted via the ratio between the switch on and the switch off time, the so-called duty cycle. However, this method can only be used in a modified form in the rotating display. This is because the time that a single pixel is displayed is very short. It is in the order of magnitude of 100 microseconds. However, a typical pulse width modulation would modulate the LEDs much slower. The solution is to control the LEDs for each pixel 8 times in succession. You could therefore say the pixels are divided into 8 subpixels. This allows the intensity of the LEDs to be varied in 8 steps. In this way, 8 times 8 times 8 equals 512 colors can be displayed. Here's a photo of a real image section. The red and green LEDs are next to each other, while the blue LEDs are radially offset. The white lines mark the transition between the macro pixels, and you can see the subpixels. Within the macro pixels, the LEDs are only switched on for a certain time. The timing of the LED control is the central challenge of the rotating display. That is why I would like to shed a little more light on the control of the LEDs at the end of this video. In this calculation, I would like to assume a rotational speed of 20 revolutions per second. This corresponds to a time per revolution of 50 milliseconds. 240 color pixels are output per revolution, and if the 8 subpixels for the color display are taken into account, the LEDs must be updated 8 times 240 equals 1920 times per revolution. The time per subpixel is therefore 26 microseconds. Let us now compare this value with the time it takes to transfer the data to the LED controllers via the SPI interface. The starting point of the calculation is the 56 LEDs. As each color LED consists of 3 individual LEDs, 3 times 56 equals 118 bits must be transmitted per LED line. The LED driver chips can be supplied at their SPI interface with a maximum clock frequency of 20 MHz. This corresponds to a time of 15 nanoseconds per bit. The data of an LED line can therefore be transmitted in 8.4 microseconds. We have to compare this value with the display time of 26 microseconds per pixel. In practice, it has turned out that the SPI transmission is actually somewhat slower. Delays occur between the transmission of the individual bytes. The cause has not been clarified yet, and it is quite conceivable that the transmission speed and potentially the angular resolution could be increased somewhat in the further development. When I introduced the monochrome rotating display, I was repeatedly asked whether the popular NeoPixel color LED could be used for a rotating display. This LED, which is also known as WS2812B, can be controlled very easily and does not require any additional driver chip. At this point, I would like to highlight 3 aspects that are important in this context. First, the transmission speed. The LED is controlled using a special transmission protocol. It takes 800 nanoseconds to transmit 1 bit. A dataset consists of 24 bits, which are therefore transmitted in 19.2 microseconds. If 56 LEDs were to be controlled, this would take 1.36 milliseconds. With a rotation speed of 20 revolutions per second, however, only 0.2 milliseconds are available per pixel. That means the NeoPixel data transfer is too slow by a factor of 7. The LEDs are cascaded. When transferring data, they pick up the first 24 bits for themselves and then pass on all further data to the next LEDs. This means that the LEDs are programmed one after the other. The time delay is 19.2 microseconds. As the display continues to rotate during that time, the result is a bent curve and not a straight line. And finally, controlling the brightness of the LEDs. As mentioned earlier, this is done with pulse width modulation. The frequency of the modulation is 400 Hertz, which is far too slow given the fast rotation of the disk. So I have to conclude that the NeoPixel LED is not suitable for a rotating display. This brings me to the end of the video. Please refer to the links and notes in the description of the video. There you will find the link to my GitHub repository where you can download all technical data. Finally, I would like to draw your attention to the copyright. You may rebuild the display for personal use the design files for non-commercial purposes. You may modify and redistribute the data as long as you give credit to the author. However, it is not permitted to use the files for commercial purposes. Thank you for your interest, and I look forward to your feedback.